Hello everyone. Okay, welcome back to CHM 577 in Organic Chemistry Part 4 for metallic bonding. So in this part, we will discuss on semiconductors. Okay, have you heard about semiconductors? Yes, right? Okay. Then, so what are actually elements that involved in semiconductors? So the answer is metalloid. Because why? Because they have a low electrical conductivity at room temperature. And second one, because of the electrical conductivity of metalloids usually increase with temperature. Okay, other than that, the gap between the valence band and the conduction band is intermediate, okay, in the size, as we have discussed this one previously in part 3. And semiconducting elements form the basis of solid-state electronic devices. So the metalloids such as silicon and also germanium are semiconducting elements whose electrical conductivity increases as temperature increases. And a striking property of these elements is that their conductivities increase markedly when they are doped with small quantities of other elements. So, semiconducting elements form the basis of solid-state electronic devices. So, for example, when silicon is doped with phosphorus, okay, it becomes an N-type semiconductor, okay, in which electric current is carried by electrons. So, N means negative. So, this is happen, okay, this can be formed when silicon is doped with phosphorus, and it becomes a N-type semiconductor in which electron current is carried by electrons. So the N means negative. Alright, and then when silicon is doped with boron, it becomes a P-type semiconductor in which N electrical current is carried by positively charged holes. So P means a positive. Right, so usually the base element that we use in the semiconductors is silicon, because you know silicon has 4 valence electrons and we uses them to make 4 covalent bonds to neighboring silicon atoms in the diamond structure. So silicon has similar structure to diamond. Alright, and then so this is the structure of the silicon, okay, where we have the sigma and also the sigma star, okay, the bonding and also the anti-bonding here level, okay. So this is where we have the valence band and also the conduction band. Okay, so what happened when we dope this silicon with group 3 elements such as a gallium, okay. So when we dope silicon with the gallium, it will produce or it will form the P-type semiconductor. Alright, then, okay, this also we call it, the P-type, we also call it as acceptor impurities, okay. Alright, so the acceptor impurities where we have positively charged, okay, hole here. Alright, as you can see in this diagram, okay. Alright, so gallium is group 3, alright, while the silicon is has 4, okay, 4 bonds surrounding here, but here we have one empty hole, okay, that it will form a positively hole and also the P-type semiconductor. Alright, then for let's say the silicon is doped with a group 5 element. For example, here we dope with arsenic, okay, alright, arsenic group 5. It means that silicon only have 4 bonds, okay, can occupy only maximum of 4 bonds. So what happened here? This is group 5. It means that it will be having 1 extra electron. For example, here, okay, in this N-type, it will form or it will be having 1 extra electron. So this extra electron that actually the main actor to conduct electricity. So in this case, the n-type you also call as the donor impurities, okay, compared to the p-type, okay. Alright, a gallium is from group 3, okay. It means that maximum maximum bond that we have around the gallium is 3, okay. So silicon, we have one extra silicon here and it will form a positive hole, right, compared to the n-type where we have extra one electron that actually conduct electricity. That's the end for the metallic bond, okay, band theory of metal and also semiconductor. So I'll see you later, okay, I'll see you soon for the next topic, and thank you and take care. Bye.